Let's get started and let's actually talk about the rotational equilibrium, as this is necessary to properly use the method of sections. And to do so, I will first draw a random truss structure for you, similar to the one that we talked about when we talked about the method of method of joints. So I'm going to use a very same type of structure here, and then we will analyze it using the method of joints. And of course, this is just the conceptual approach here, and in later slides we will actually use the methods to find our numerical answers to problems like that. So here I have a system that is simply supported, and I should just give it nodes A, B, C, D, and E. And also, for good measures, remember that these are all hinges technically, although we usually don't show them at the end anymore. And a very common question now would be, hey, please find the internal forces in, let's say, ED, BD, and BC. And if you remember how we did it with the method of joints, so if we would use the method of joints and we would find our external support reactions first, then we could, for example, start to calculate these member forces here at this node and then bring our forces up here and move our way into the structure and around. And as we already talked about last class, the method of sections is a little bit complicated when you have larger and larger structures, because you have to work your way in from the outside. And with the method of sections that we're talking about here now, I can in one scoop really release 3 internal forces, because now I have the rotational equilibrium. But I want to explain that to you now in more detail. So I can now pretty much release the entire system on one side. So for example, on the left side, and have this cut, I'm going to call this cut 1. But I also could have done it exactly on the other side, which is cut 2, and to no surprise, both of them have to give the same results. But to clarify that a little bit more, I will now draw the very same structure separated at that cut, and that looks like this. So I have the left side cut here and the right side cut of the structure right here. And by doing that, I effectively separated and released the internal forces at those locations. So I will now introduce my internal forces, which are only normal forces, just like we talked about before. So I have a normal force in line with each member. And those are usually similar to the method of joints. They are assumed to be in tension first. So I'm going to do that right now. So I'm going to assume this here. This would be DE to be in tension. BD would be also assumed to be in tension. And BC would also assume to be in tension. And if that's the case, then I have to do it on the other side the same way. Of course, this is also DE. I have BE here, and I have BC here. And so now we probably already understand that we can separate these structures and we can cut, because remember that in mechanics the cut always works as long as you bring the forces back in that you released. And now we have to find out how can we generate equilibrium for each of these cuts, because remember, equilibrium must pretty much exist for this system here, just as it has to exist for the other side system. But to do that now, we can try our regular trick, right? So we can try our sum of the forces in X is equal to 0. And if I were to do that now here for the left cut, let's say, then I had plus DE minus BC, or also plus BC in this case. And so I have 2 unknowns. But let's just write that down for now. But before I do that, let me introduce the support reactions as well. So RAY, and here we of course have RCY and RCX. How to calculate those is not part of this lecture, but now I have all my external and internal forces, and I'm just gonna now go back to this equation here. So the sum of the forces in X is equal to 0, and 0 would be equal to plus DE plus BC, but also plus BEX. Right? So we have first DE, BC, and also the X component of BE. So we have one equation with 3 unknowns effectively. So that does not really help us as of right now. Let's try the sum of the forces in the y direction being equal to 0. And 0 is equal to, and again, I'm looking at this left cut here. Of course, it's true for the right side as well, but I'm looking at the left side. So 0 is equal to plus RAY, which usually would include a value. And then the only other thing that has a vertical component actually is BE. So we would say plus BEY. Right? So let me clarify that real quick. So BE has, of course, a horizontal component and a vertical component. And in this case, since we assume intention, they go to the right and up first. And so now you can tell already from this picture that BE would have to point down against RAY. But even if I can solve this equation now, so this is solvable, right? So this equation is solvable. So let's make that note here. So this is solvable. But even if I find BEY, then what I would end up with is solving BCX, and I still have my 2 unknowns here. So therefore, I reached an end pass, and I need to find another solution. And of course, from the introduction of the lecture, you already remember that now I'm using the moment rotational equilibrium to solve this problem. And this is where the trick in the method of section lies. Remember that when we find the sum of the moments about a point, we usually, when we find, for example, let's say RAY, then we usually take the sum of the moments about C. And the reason we're doing that is not because it wouldn't work at any other point. In fact, the sum of the moments about any point needs to be 0 in an equilibrium system. But the reason we're taking the sum of the moments about C is because RCY and RCX disappears, and we only have one unknown, which is RAY, when we rotate about this point. So this is a condition that's always true, right? So if you find any point in any structure where all but one unknown disappears, then you can easily set up one equation with 1 unknowns. And so if now I start to use the sum of the moments here as my third equation, sum of the moments being equal to 0, I need to find a very interesting point to rotate about. And so the question is, which of these ones here, or where would be a point for this cut to take the sum of the moments about, so that like I only end up with 1 unknowns. And if we look at that, we have 1, 2, 3 unknowns, but 2 of them meet in 1 point. And in fact, you can tell that from the way I named them. So there's BE and BC. They share one letter, the B, and therefore they get together at this point. And that means if I take the sum of the moments about this point, then the only unknown is DE. So let's write that down, how that works. So I would take the sum of the moments about B, and let me just also include some dimensions here, or some random dimensions, if you will. So I probably need this dimension from here to here. I'm going to call that A. And then I will also need the vertical dimension, which would be along this line. So that would be here and here, and I'm going to call that B. All right. So now what I end up with is 0 is equal to, and I'll say that again, we're taking the sum of the moments about point B, so about this point here. And so I have RAY that has a lever arm about this point. I have DE that has a lever arm about this point, but BE and BC do not. So therefore, I'm going to start with my unknown usually, which is DE in this case, DE. And that is multiplied by B. And I need to, of course, obey to my rotational sense. So this here turns clockwise about point B. So therefore, it's negative. So negative DE times B. And the only thing that opposes this in this particular cut is RAY times A, right? Because it has the distance of this chord here on the bottom. And I just named that A. So if I write that down, that would be RAY multiplied by A. And in this case, RAY rotates counterclockwise about B, so therefore it happens to be positive. And because there's only effectively one unknown now in the system, right? So the only unknown is DE, and therefore I can solve this. So I can solve this for you right now, but that's not really the point of the concept here. So DE would be equal to RAY times A divided by B. And that I can solve now. And now you can see that I have also solved now for DE. And so I can use that DE in this equation up here. And then last but not least, I could solve for BC, which is my last unknown in this equation now. So I can solve this. So that technically concludes the method of sections, but let's make sure that we really get the concept, and let's actually look on the left side and cut 2 here. So in cut 2, this works as well. And if I wanted to find DE as well, then all I would have to do is find the point where the other ones disappear. And it is still true that it's at node B, except that node B now is outside of this cut. And that is often confusing to students, right? But there's no difference, because the sum of the moments about this point, 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 any point is equal to 0. So you cannot get confused, or you should not get confused by the fact that the point about which you rotate the system is actually outside of your cut cloud, as I call it, right? So I call this here my cut cloud number 2, and it's outside that rotational point. But for clarity, I'm gonna draw the structure just with like dashed lines here. That's often how you see it in books. So I will use my ruler here, and I will pretty much designate this here as point B. This is the point B, or node B, which is outside of my cut. But let's set up the equation for that one. And I'm going to do that up here. And so I now need my dimensions again. So because it's a symmetric system, at least in my head it was a symmetric system, but I'm going to also call this here direction A, and the height is still B. Or I should have called it H, but it doesn't really matter. So this is B. And it's the same as it is on the right side. So just to be clear, here on the right side, I have these 2 dimensions. So the entire system is pretty much 2A long. So from here to here, we have A and A. And then the height is B. So now you know for sure what's going on here in the system. But let's set up the sum of the moments about that point here. So the sum of the moments about this point, which is again outside of the cloud. So to find DE, I will say the sum of the moments about point B is equal to 0, counterclockwise positive, and 0 is equal to, I start with my unknown, dE multiplied by B, and that is turning counterclockwise, therefore it's positive. And now I also have to consider RCX and RCY. RCX actually points right through this, the line of action of RCY is going right through that point, so that goes to 0 once again, but RCX has a value. And so RCY multiplied by A. And that rotates counterclockwise, therefore it's also positive. Right? And I can solve this now for dE. So dE again is RCY multiplied by A divided by B. And to be fair, like, we have not included any force on the top here, or like any external force except the support reactions, but you would just include them. So I'm going to do that now just for your study notes here. So let's say I have a force F1 here. Then that would be only in the cut number 2. So you would find that here as well, F1. And of course, that would have an effect on your support reactions, and we didn't calculate those right now. But it would be reflected in RAY and RCY. And so in the equation that we wrote down here, it would have no effect, right? Because for this equation that we wrote down here, we only worried about this cut on the top left. Whereas for this cut here, we include F1. So I would have to add this here to my equation, and I'm going to do that for you just for good measures and to have all the possibilities covered here. So let's see where we would add that. So we would have F1, and that would now be technically multiplied by A over 2, right? Because we assume that node D is exactly halfway between node B and C. That's not very precisely drawn here, but that's usually how those structures are geometrically arranged. So F would be right at this point, returning about this point, so A halves. And in fact, it's turning it's turning clockwise, so therefore it's a negative part. And so I also need to include that in my equation here. And so if I substitute that, then we would have RCY times A minus F1 times A, and all of that divided by B. Sorry, this is A over 2, right? And all of that divided by B. So that's how dE would look like if we had the force in there. But I think the general concept here gets clear, and that is that you can cut the system anywhere you want, except you have to worry about no more than 3 members, right? So we can only cut through 3 members and not more, because we have only 3 equilibrium conditions. But as long as you cut through any 3 members, preferably through 3 such that 2 meet in 1 point, then you can always apply this method. And that is the method of sections conceptually. We will, after we talk about the zero force members, we will actually use this in action and calculate some numerical values. But first, let's talk about zero force members.